Hello, everybody. How we doing? Welcome. It's great to see some familiar faces in the chat. How's everybody doing? If you're here for the first time, I should say, welcome as well. Also, let us know if this is your first time joining us. That'd be great. Feel free to say hi. Fearless leader is a little bit terrifying. All right, Anusha, welcome. Glad you could join us. We're going to do some material today that has a little bit of overlap with a couple other projects that I work on. And one of those is our bioinformatics algorithms project. So we have a textbook all about how to apply algorithms to computational biology. A lot of what we're doing here is going to be inspired by what we do in the initial chapter of that book. So if you're interested, we're going to also be covering it a little bit in our Great Ideas in Computational Biology course. So we're going to have another course downstream of this where we talk only about computational biology and the methods that are useful for analyzing biological data sets. We're going to finish up our chapter tonight too. So this is going to be the capstone, the culmination of what we're talking about right now, which is where we find hidden messages in bacterial genomes. And next time we're going to start a new chapter. So go to programmingforlovers.com where you're going to find a reading to prepare you about what we're going to do next, which is all about Monte Carlo simulation, which means generating a bunch of random trials in order to simulate something. What we're going to apply it to, we'll see a couple different examples, but our big application is going to be building a simulation of a presidential election using polling data, something that's had a ton of practical stuff written about it. And I think it's going to have a lot of connections to things like prediction markets and all these sorts of things that are current today. What else? Tonight's going to be a challenging session, which is good. What is it they say? We can do hard things. And what's nice about it is that some of the material is really going to be somewhat of a review. Others of the material is going to be an example of we can state a problem that I think is really like one little step beyond what we do. But what we're going to see is optimizing this algorithm that we make is going to take us in a lot of different directions. So if you love a challenge, BZ, I'm glad you're here. This is the time for you. Now, what else? That's about it. I think we're nearly ready to get started. We have a couple other things though, which is we have supers unlocked now, whatever that is. So we've had a lot of really good interest in the channel, so it's been great to see. And so I was thinking, I didn't realize there are now like super chat goals. I don't have one established, but if you have ideas for that, let me know what you think, because that's something we could do. Most importantly, though, it does appear, so for repeat viewers, we have a special guest here tonight, which is that either we have an imposter or my mom has somehow managed to locate the chat and has told everyone good evening. And I'm a little bit disappointed that no one noticed that and made sure to give her a welcome. So let's make sure. I don't think she saw the welcome that we gave her last time. So all of our repeat folks here who are always here, let's continue to appreciate her and make her our celebrity of the night. So yes, Mom, welcome. I like the idea that we should have like a super goal where it involves me like getting a green screen suit, and then you guys have to tell me what I have to wind up being, and then I've got to explain to my mom why I'm a waifu on a YouTube live. But we're going to take things one step at a time, and today was a big first step. So thank you, Mom. Good job making it to the chat. And yeah, I'm glad this didn't conflict with pottery class. So in the meantime, let's get started. As I always say, like and subscribe. You can look at our individual videos. So we have upcoming lives. You can always make sure to get notified about those. We have a soft deadline. So what we did previously on working with integer functions. All of the exercises on those are due this week. So we have some office hours for that. Go over and hop in our Discord, meet each other, use this as an opportunity to get help with each other. And then we have office hours as well. So whether you want to just support or come and have some deeper experience, we'll have an office hour on Wednesday night before things are due. And I'm thinking about also just sort of hopping over to Discord on Thursday night before the homework is, or the practice exercises are complete. So we'll have that for our fellow math subscribers, and there's links to that below. But in the meantime, I think we're ready to get going. Thank you so much for all the positivity in the chat. And yeah, I'm excited. So we'll get started here. The last time we were together, we looked at this fundamental biological problem. And that very, I think, fundamental or straightforward biological problem is how many times does each substring of a certain length occur in a longer region? So a region might be somewhere where we know there's going to be a protein that comes in and binds to this particular location, but we don't know exactly where. And what we saw was if a protein is binding to a region of DNA, from an evolutionary perspective, it's probably occurring relatively frequently. And so if we know where to look, we can look for this specific sequence. What we want to do is to scale to the entire genome and find every possible substring that occurs multiple times. And so that might seem like a hard problem. So I'm saying I'm going from a region that might be 500 nucleotides to a genome that might contain like 5 million nucleotides. But at the end of the day, a lot of times what we see in solving problems with programming is that if we can solve something for one case, one particular instance, a lot of times we can just stretch our solution out over a much larger region. So if we can do something once, we can do something n times, in other words. And the thing that we can do once is find these frequently occurring substrings within a longer string. And we just need to expand this approach to apply it over all of the possible windows of the genome. And so we'll do this, and then we're going to apply it to a real genome. And the function that I'm interested in, and these functions are, what we cover is taken from our preparatory reading. But the function that I'm interested in is going to be called find clumps. And here is a great example of where, I might actually write the doc string first. So on a high level, what is it that this function is going to do? It's going to find all substrings of a given length in a longer string that occur more than some threshold number of times within a short region. So on a high level, before I haven't even specified anything about parameters, right? But I'm saying that's what we're doing. And then I can say what my parameters need to be. So as input, what I'm going to say is, well, we need a text. And you might imagine, we could frame this as a text or a genome. Imagine this could be more general than a DNA data set. There's nothing special about the ACs, Gs, and Ts. Perhaps this could be portable. So I'll take a text that's a string. And I need to also have a K that's an integer. And I'm going to have a window length parameter that's also an integer. And then a T that's an integer. And I'll put all these in my type hints here momentarily. In the meantime, I want to say, what is it that I return? Okay. And I can be very precise here to say, at the end of the day, I'm going to return a list of strings. And you could imagine you could do this in a slightly different way. I'll make a comment there momentarily. But what we're really doing is we want to return a list of all the strings of length K that occur at least T times within a window of window length. And I should say window. And by window, I mean this is a substring. and it's a substring of text. So we've now specified completely precisely what it is that we want to do. And this means that I can go in and I can update my type hints too. So I can say we care about text as a string, k is an integer, window length is also an integer, and the threshold, which is why I'm calling it t, the threshold number of occurrences that you need to see of a substring in order to say it occurs frequently, it's a clump, is going to be called t. Then at the end of this process, I want to return a list of strings. And I said that might not necessarily return a list of strings. Maybe that what it returns is somehow an assignment of the strings themselves to the locations where they occur in the text. But let's at least start with solving this problem, and then we're going to see what we need to do. Oh, no. The next thing we might say is where it's important here to think through what might our errors be. And I actually think this is a great opportunity for me to give you the exercise and say, what do we need to check in terms of errors? Because things like types, doc strings and type hints, these are important stylistic things. But another thing that we should be focusing on equally is to think about all the different cases that we don't want to allow and where we explicitly want to provide an error message or where we immediately want to return something. So my question for you is, what are the types of things that we should check in order to make sure that the parameters that we're giving as input to this function are actually valid? Yeah, number one from Remy and BZ. Good. The first thing we should do, and I'll look for other examples as we go, but probably if k is less than or equal to 0, that would certainly be bad. So if that were the case, we should raise a value error, and we should say error k non-positive value of k. All right, fair enough. I like that we want to check also k compared to the length of the text. I think that's really good. So we might say, what happens if k is longer than the text? That doesn't make a whole lot of sense. So in this case, I would say, well, maybe you have a value error. Maybe, though, you just acknowledge that k is longer than the length of the text, so there's no way that there could be a solution here. What I'm going to do is I'm just going to return an empty list. But it's sort of a decision that we could make. And I think if k is less than or equal to 0, that would be bad. I'm just going to add a bunch of ors here to say if the window length is less than or equal to 0, that would be bad too. Or if t is less than or equal to 0. And I could say error non-positive parameter. Okay, so I'm combining three things there. I probably should do individual tests, but just for the sake of simplicity, we can combine all three of those. That's good. We had an empty text. That's also good. So if length of text is equal to 0, I could raise a value error there and say error empty string given. Good. And I'm impressed that we actually saw a couple of other folks note that k needs to be less than or equal to the window length. So the final test that we might have would be if it's the case that k were greater than the window length. Sorry, excuse me. So that doesn't make a whole lot of sense. And here where we could do the same sort of thing, you could raise a value error. I guess I suppose that you could also return an empty list. But in either case, we need to make sure that we're checking this. So this would be bad. All right. And that shows you just how, look at how many lines we've written, and there's no real code here. We have a couple of if statements to check parameters for sure, but most of this is just making sure that we understand how the function's going to work and making sure that we're handling error checking, and this is a critical part of programming that we're going to see as what we do gets more complicated. This isn't going anywhere, but it's also requires us to think carefully. And so it's just as important as anything else in programming. But in the meantime, how is the function going to work? So the function will work by saying, okay, well, what am I returning? I'm returning a list of strings. We know that. So let me make that. And in advance, I don't know anything about it. I'm going to declare patterns to be an empty list. And then at the end, I'm going to return it. I don't know how many patterns are in this list to begin with. Every time I encounter a pattern that occurs more than the threshold number of times, I'm going to append it. Now, a couple things. Number one, I need to be careful with that because whenever I encounter a pattern, I need to make sure that I haven't already added it. I don't want to add a bunch of duplicates. We're going to say more about that later. The other thing I want to say is, just as we saw there's a special way of declaring a dictionary to be very precise, I know this is going to contain strings. So it might be the case if I had something with mixed types in it, like a list, and it had integers and strings and planets and all sorts of stuff, then I would declare the list like this. That's fine. But I know that my list needs to be a collection of patterns. So there's a way of declaring this list that allows me to indicate that, just as we did for dictionaries. So I could say it's a list of strings and it starts off as empty. The next thing I might say is I need to know how long the text is. That's just for the sake of simplicity. A lot of times, as we've seen, just setting n equal length of text just gives us some peace of mind, if nothing else. Now, the next point I want to say is we've got everything declared here. We need to, at the highest level, because what I want to do is I want to zoom in on a window. But in order to zoom in on a window, I need to be able to scan across all windows of the genome, or the text that I'm working with. So I need to range over all windows having window length of text. What is my ranging? That's my question for you. How many of those windows are there? The hint is that, well, a window is a substring. Good, so this is, John's got it. This is something that we've seen before. We know if we're ranging over the windows are just substrings of the text. But before, we've had substrings of the text of length k. Here, we just changed the parameter. So this allows us to practice what we know, which is that if we want all substrings of text having length, window length, well, you need to range some parameter, which we're going to call I, from 0 up to n minus the window length plus 1. Okay, so we've seen this before with n minus k plus 1, and yet again we get to apply this formula that says the starting indices of every k-mer, or every substring of length window length, are going to range from 0 up to, but not including this, so the last index is going to be starting at position n minus window length. When I range over all of the windows, at each position, what I want to do is catalog the number of counts of each k-mer in the current window. So at this point in time, I can say the current window is equal to, well, it's the substring of text that starts at position I, and I know how long I need to be. The window has length equal to this window length parameter. And here's where we get to apply our substring indexing, and we know that the top index minus the bottom index needs to be window length. So I can simply say that the top index needs to be I plus that window length. And now I have this current window. All that remains is to say, well, how do I catalog all the counts of every Kmer in the current window. If only we had an approach for doing that. And here's what I was getting at the start when I said, a lot of times if you can do something once, you can do it n times. And we're not quite doing it n times, we're doing it n minus window length plus 1 times. But the point still stands that what we need to do is to just say, I've got the frequency table, and I want to give it the current window and a value of k. This is a function that we wrote last time. This will go through and say for every Kmer, form a table that's going to say, here is each substring of length k, and it maps to the number of occurrences of each one. That's really useful because I've already got that function and stand by on how we're going to access it. But then once I have that frequency map, I say, I've got the frequency map, what occurs frequently? Meaning more than or equal to t times. And I can say, well, I can range over the frequency map and simply identify everything in that frequency map that has a value that's greater than or equal to t. To do that, I'm just going to say for some string s and a val. We learned when we first started working with dictionaries that if the frequency map is this dictionary that maps strings to integers, I can range over the strings and the integers in one range with the notation in frequency map dot items. So this will give me the current string that I'm interested in. This will give me the current value that corresponds to that string, which is its number of occurrences in this frequency map. Then I say, okay, if the value is bigger than or equal to t, I'm going to append the current string to patterns. So if this is the case, I found a clump, I should say, because this is a string that occurs at least t times within the current window. So the frequency table is formed from the current window. All that I need is one of these windows where it occurs at least t times, and that is good enough for me to say this is a frequent pattern in some short region of the text that I'm working with. Now my question is, this function is incorrect. What am I missing? I hinted at it earlier, but what is it that this function is actually missing? It says t, we've got t, so I'm checking if the current value is at least equal to t. We use t, but it's a good point that we always want to make sure. Here's a critical learning point for all of programming. If I specify 4 input parameters, I better use every single one of them. You can go through here and say, well, we're ranging over these windows, we're accessing text, we're accessing k here by giving it the frequency table, we're checking if it's t. And we're using the window length, of course. So we use all of them. John said double ups. Okay, that's a good point. So I want you to imagine that we slide this window along the whole string. And you may imagine that, well, I'm at a certain window. And then if we move that one over, if something is frequent in this window, it's probably frequent in this window that's just next to it. Imagine this window has length 500 and you're looking for something that occurs, I don't know, 3 times. If it occurs 3 times here, if I move over one symbol, it probably occurs there too. So the issue becomes, I've not checked to make sure that it's already hasn't been added to the patterns. So this is going to add a bunch of duplicates in practice. And so I need to be careful about this. If I've seen S before in the patterns, then this is going to be a duplicate. And we can handle this by saying, have we seen it thus far? So when I check my if statement, I need to check 2 things. So check to make sure that the value is at least equal to t, and also that I haven't already added s to the patterns. this is something we can check. So value greater than or equal to t is good. I also want an and. Here's our opportunity to use and. And I'm going to say, is it the case that, well, I want to check, is S in patterns? But I want the opposite of it. So if that's equal to false. So is it the case that when I look at, I should have this, I only want to append it if I haven't seen it, meaning that if I were to look and check this is S in patterns, I don't want that evaluating to true. If this evaluates to false, that's exactly what I want to say. So S in patterns equal false means that I have not seen it before. We can do this in a simpler way though. So one of the things I could do would be to say something like not S in patterns. So just take the opposite of what we want. And now I'm checking S in patterns. If that's false and I take the opposite of that, I get true, and that's what I would want. Okay. But one of the things that's nice about Python is we're able to write things like this in more human language. So Python is actually okay if I do not in, S not in patterns. And now that looks so clean and comfortable because this is what I want to check. Is it the case that S is not in the patterns, as well as the fact that I want to make sure that the value associated with S is sufficiently high for it to be considered frequent. All right, and some good questions thus far. So there's one question about, could we use a set? If you want to see a set, sit tight. We haven't introduced sets as of this point in time. It's going to be an opportunity for us to motivate it. However, I'm going to make a point about this when we encounter it, because you could do really well, not necessarily in this implementation of the algorithm, but really well without actually needing a set. That's a great question. Hang on to that. And another point is, well, frequency table is underlined. And the reason why it's underlined here is because I haven't actually written this function within the file that we're working on. That's not great because I know I've already written the function. And so the point becomes, how is it that I can get it into the code that I want to work with? And there's a lot of ways to do this. And one of the things that I think maybe other languages might get right in some cases is it seems like it should be easy to just say, Python, go look at the frequent words folder and acknowledge that in main.py over here, I've got a function called frequency table that I want to use. And yes, what I could do is copy it over. And I've told you, anytime we find ourselves copying code, we probably should feel a little bit icky, because why not just maintain one version of this? And then we can use it whenever we want. We can import it and bring it in whenever we want. Doing that is going to take us a little far afield for what I want to cover right now. So for now, I'm going to say, well, what we would like to do is use it within what we have. And something I could do is simply to copy it in here. I'm going to move us a little beyond what we've done thus far with working with only a single file in each folder. And I'm going to go into clumps and I'm going to create a new file, and I'm just going to call it helper.py. And this is going to indicate that I have helper functions within this. I could call it anything I like, but I'm just going to call it helper from now. And now if I go back to main and I want to access frequency table, I can go up here and import helper as if it were a package or something, like importing math or importing time. So I can do this just by saying, well, from, one thing I could say is import helper. And then when I import the helper, and then when I call the frequency table, it comes from helper.py within the same folder. And so I'm just going to say helper.frequency table. That's how we're used to calling functions that come from time or math or something that's a package that we're importing at the top. We can do a little bit better than this. Typically when we're working with a bunch of different files in the same folder, I'm just going to import the specific function that I need. And so a nice feature is to say, from helper, I just want to import one specific function for this implementation, and the function that we want is called frequency table. So from helper, import frequency table. And now I won't need to call helper dot frequency table. I'm just going to call frequency table. And now you see it automatically gets colored as yellow to indicate Python can see the function and we're in good shape. The next question I would have, here's another question for you. When we look at our function, ignore for a second the error checking and the fact that the doc string is long. All that is just necessary. If you look at the meat of the function though, which is here, is there anything we could do to make this more straightforward? And I don't necessarily mean use a fancy data structure that's included with Python. But is there anything we could do to simplify our code? And what I want you to think about is, one of the things I have said up till now is that I'm not personally, and there's a lot of folks out there who feel similarly, I'm not personally tremendously wild about nesting multiple layers or multiple levels of for loops and if statements. And if you look at this, you've got a for loop here, got a for loop here, and then you've got an if statement within this. What could we do instead? Any ideas to simplify this down? Good. So I'm seeing there's often just a small number of answers in the class. One of those is mutability or immutability, as the case may be. Another one that's going to come up all the time is subroutine. You'll hear me say that word 100 times at least throughout the course of the class. As well as be lazy. Yeah, we know all these things. In this particular case, there's a natural way of having a subroutine here. And the subroutine that I could identify would be to say, well, as I range through the windows, I set my current window. That's my substring I care about. I make the frequency table for that particular window. And then I could just say something like, I don't know, patterns equals add new frequent strings of the frequency map. And then it needs to take other things. So it needs to take the collection of patterns that I currently have. And then it needs to take t, because it needs to know how frequent does something need to occur in order to be considered, more than or equal to the threshold. And then none of this is needed. All of this could just get moved out into a subroutine, and now the function gets that much tighter. It's actually only like 10 lines long. And I could go that way. And there's absolutely nothing wrong with doing that. In fact, I would encourage you to do that. I'm not actually going to do it right now for a reason that's going to become clear in a little bit. And so this, I think, is a better way of going about it as you start to implement this, but it's not something that I'm going to do. Okay. So say we could use a subroutine, and it's a good enough idea for me to just keep it commented out. But that's not the direction that we're going to go. For now, the direction I want to go is, I've got an algorithm. Let's make sure that it's working at least on small data sets, and then if it seems to be working well, let's apply it to a real genome. Now, let's go into main. We're going to find clumps. And we just give it text equal. I've got it something that where the answer is going to be obvious. So we have a bunch of A's, CGCT, and then a bunch of more A's. Okay. And then K is equal to, 2. The window length could be equal to 4. And then the threshold number of occurrences is, I could set 3. I could set 2. And I could vary this, but what I want to do is just call find clumps of text K, window length, and T. And then I can just say total number of clumps. Well, let's just print clumps. It's not going to be a lot of things. Okay. And we've got our code. So now we've got a function. We've got a little bit of code in main. We're going to do what we always do. I'm going to bring up a terminal. And then we're going to say, let's navigate where we care about, which is into src and then clumps. And then I'm going to run my code by calling Python 3 because I'm on a Mac. If I were on Windows, it would just be Python and then main.py. What did I not do? Cannot import name frequency table from helper. I thought I had it. Oh, I didn't save it. Ooh, I was so worried. I was like, Python has failed to comply. So make sure you always save your code, kids. And that fixed everything here. So we see there's only one clump of length 2. It's AA. And I could plug a million different tests into this. And that's, I could spend 30 minutes on that. That's not so much what I'm interested in doing. What I really want to do is just get a real genome and apply this algorithm to the genome. And so to do that, we're going to work with E. coli. E. coli is like 4.5 million nucleotides, and that's pretty large. It's not a string I want to copy over. You might find it challenging to type all that out. What would be better is to just import a package that's going to access this string, this genome somewhere, at a URL. And so what I need is a requests package. This is going to allow me to, within Python, as long as I've got an internet connection, read from a file somewhere on the internet, pull this in, and then store that file, convert it to a string, and feed it into this algorithm that we care about. But the package that I want to work with is called requests, and we can make sure that it's installed if I run pip3, or if you're on a Windows machine, pip install requests. So we've seen how to install packages before, and I've already got it installed, so it'll be quick. Your installation might take a little bit longer, but once I've installed that using pip, then I just need to say, let's import the requests package that I just installed. Once I've got that, that's going to allow me to do something like to say the URL is equal to a string. At the end of the day, it's a web address, and it's just a string that I want to work with. And the string that I want to work with, here's where I've got something I'm going to copy over. So this comes from our bioinformatics algorithms project, which I mentioned. And if you just go to bioinformaticsalgorithms.com, it'll take you to our textbook website if you want to check that out. We've got like 5 chapters you can read for free. And this is one of them where we delve into this particular problem and go in a slightly different direction than what I'm doing. But we also have some data stored there. And a lot of times when you store like genomes, they're in certain file formats and so forth. But we just have this as a text string there. So you don't have to write a parser to make sure that you're eliminating any additional data in the file. This is just stored as a string of text. And when I've done this, after I've declared my URL string, I want to make sure everything was okay. So I want to read in from the URL. I want to say, when I read from the URL, it's going to give me a response. This is sort of a preview of object-oriented programming. I don't need to take this detour at this moment in time, but we're going to read in from this URL. It's going to give me this response object. And I'm going to read in by saying requests, meaning access the requests package that I just installed. And then .get is going to go in and read the given URL. So I need to give it URL as an input. Then I've got a special function that response can call. That's going to be called raise for status. So I'm going to say response.raise for status. And if anything happened, this is going to give us an error. Okay, so if there were any issue there, if anything went wrong, that's going to go ahead and satisfy that for us. In the meantime, if I make it there, so if I make it to this point of the code, I know everything is okay. And because of the way I wrote the file, it's just a text file, it's just a bunch of ACs, Gs, and Ts, I can go in and I can access a field, an attribute of response called text. It's a little preview of object-oriented programming that we're going to see soon. For now, just telling you that this goes in and accesses the string from the file. And so that's our genome. if we want to make sure everything works, I'm just going to say that the length of the genome is, and then I'm going to say length of the genome. So I'm going to go to clumps. I'm going to run python3 main.py. So I'm going to go up 2 times. It reads it in pretty quickly. Thank you, Python. And it tells me that this genome has 4,639,675 nucleotides. I could print it out. That's going to look pretty ugly in the console. And so you just have to trust me. You can go and look at the URL and you can see it is indeed A, C's, G's, and T's. And they're taken from a biological data set where you can go and get lots of different bacteria. But we got E. coli since it's the model organism that we work with when we work with bacteria. Of course, I don't want to just print the length of the genome. I want to run my clump finding algorithm. And so if I want to run my clump finding algorithm, let's give it some more realistic parameters. So in this case, k is equal to, say, 9. And that was what we looked at in a previous code along where we were saying this length 9 substring was occurring frequently and indicating that this was the binding motif within the bacterium's replication origin. So we'll use the same parameter. That was a length 500 window. And the threshold that we're interested in was t equal to 3. We also had a few reverse complements in that region. But let's look for everything that occurs at least 3 times in the genome. So we have 4.6 million nucleotides. We're ranging a window of length 500 over the genome. And we're saying anytime we see something occur more than 3 times, we're going to consider it a clump. So I'm going to update my clumps. I could say clumps E. coli equal to find clumps. And here, the parameter order is important. Fortunately, I can see it in front of me. It's genome, K, window length, and then the threshold parameter that I care about, which is T. And at the end of this process, I want to say, well, how many total clumps did I get? I'm going to say we have length of clumps E. coli, and then I'm going to say total clumps. Okay. Now, I'm going to save that, and I'm ready to run. So after I save, I'm going to hit up again, python3 main.py, and when I run it, we're going to get a very Pythonic result. What is that very Pythonic result? It's the open cursor that we're just staring at. So I think, well, maybe I've got an infinite loop. Maybe I've got a bug. I don't really know. I'm probably going to be waiting for a little bit of time. So if I tricked you into running this along with me, I'm going to Control-C and interrupt everything. That was the particular line it was on when the code got halted. And I could do a couple of things. So for one, I need to check and make sure that something is happening. And one of the ways, here's a classic way that we can do it, is especially when we're working with relatively straightforward functions, and we just want to make sure that that something is happening, something's executing. I'm going to go and put a very, I'm hesitant to teach you to put in print statements into functions that are presumably okay. But what I'm going to do is when I range over all these windows, every time I hit something that's divisible by a certain number, and the number I'm going to pick just out of thin air is 1,000, then I'm going to print, hey, we're on step number whatever. So that's not hard. I know how to see if something's divisible by 1,000. So I'll say if I% 1,000 is equal to 0, then I'm going to print executing I equal to, and then I. So that now when I save that and then I run it, we're seeing that something is happening. And it's covering, thousands of these, 100,000 in a few seconds. But the problem is this is not going to scale that well if we're working with genomes of length 5 million. And if we want to run this a bunch of times, you're thinking, at the end of the day, there's nothing very, very complex about what we're doing. It just feels like the function should be faster than this. And part of the problem with that is that Python is just inherently a slow language. But part of the issue is that there's a faster way of writing the function. So we're not going to quite get, I don't want to sit and wait on this thing. It's barely 10% finished at this point. I don't want to sit and wait on it to complete. So I'm going to Control C. But I can see that it is working. And in the meantime, what I want to do is I'll remove this for a second since we can see it's at least running. And I would like to find a way of optimizing the algorithm that I have. The first thing that we always want to do is to have something that's functional. There's nothing wrong with what we've done. There is a if you don't believe me, there's a famous quote from Donald Knuth who said, about 97% of the time, premature optimization is the root of all evil. And he's way smarter than me, way more accomplished than me, and I'm going to trust him on that. And it's a complex statement because he does say 3% of the time, it's not that bad of an idea to optimize prematurely, but most of the time, we don't want to optimize something right out of the gate. It's just a pathway to everything being complicated. Coding is hard enough. Let's just write something that works. There's nothing wrong with that. But I do have a question for you, which is, how do I make this algorithm better or faster? Certainly we could use a subroutine. We talked about that. But we've got our algorithm where after we do the error checking, we form our list of patterns, we set n equal to the length of the text, and then we range over all of the windows, form the frequency table of the current window, and then check to see, have we seen it before? And is it greater than or equal to t in terms of its number of occurrences in the current window? And if both of those things are true, we append it to the list of patterns, and then we eventually return the list of patterns. What ideas do we have on how we could make that faster? Are there things that we're doing that aren't great? John says, make less than 5 million frequency tables. All right, I like that. I have an English teacher who would say, John, you need to say fewer, but I'm not going to say that. I'm happy with that idea. And we're going to say, why is it that we make 5 million or 4.6 million frequency tables? Is that a good idea? And that, because that's the meat of what we're doing. That's a lot of frequency tables. And you might think, well, I need all of those frequency tables, right? But let me think about what we're getting at with this, which is that when I slide the window over one letter, so when I'm doing this, I'm taking the window that's maybe of length 500, say, that starts at the first position of the string, and then I slide it over one letter and look at the second position, then it goes one more to the third. All those windows are very similar, especially if you look at the k-mers inside of them. They're going to be pretty similar to each other. And I'm going to give an example of this. So let's outside of the function. I've got an example. Okay. My text is going to be called banana split. Right. Partly because I'm hungry, also because the banana split was invented in Western Pennsylvania, so it's a proud local heritage point. But let's say I have the window length is equal to 6. Right. And let's look at what the first window is going to be. So this first window is banana. So we have a substring called banana. That's our first window. And then we say, let's make k equal to 3, something like that. So you've got 4 substrings in there. You've got BAN, you've got ANA, you've got NAN, and you have another ANA. I did it on purpose so you'd see there's a little bit of repeat. So our frequency table is going to be BAN 1. And I should say, let's do it this way. First frequency table. BAN is going to get a 1. ANA is going to get a 2. And NAN is going to get a 1. Now let's look at the second frequency table. When I go from here, and then I now have ananas, okay, then the next frequency table is going to be very similar because all I lost was a BAN off the front, so this no longer will be there. But if I look at the first 5 letters, ANA, NAN, and ANA again, are all going to occur. The only thing I'm going to pick up is a NOS. So the second frequency table is the exact same. ANA occurs twice. NAN occurs once. The BAN no longer occurs, but now I have NAS. It's going to occur once. So far, so good. So these elements are all the same. These are all the same. You lose one k-mer, you pick up another one. So it doesn't really make sense to keep regenerating the frequency table. What our algorithm is doing is every time through, it makes the frequency table, and then it's like, oh, that was cool, and then it throws it out the window, and then it moves the moves the window one nucleotide over, generates the whole frequency table, says, oh, that was cool, and then throws it out the window. So there's no reason to not remember the fact that at every point in time, you're only losing one k-mer and picking up one more. So I want to have the same exact parameters. I want to have the same error messages, the same doc string, everything. But I'm going to have another function, and because I'm not a tremendously creative person, I'm going to call it find clumps faster, right? So I hope it's faster, but here's our algorithm. The question becomes, how does it change? So all the error checking is going to be the same. And really, I probably could just, copy all of this over, because it's going to be similar too. And at least use it as a guide. I want to be careful with copying code. But I know that patterns is going to be an empty list of strings. I know n is going to be equal to the length of the text. And then what I want to do is range over all the windows, but I want to be careful because there's only one time that I actually want to call the frequency table subroutine, and that's for the first window. So the first window that I care about is going to be equal to the text of window length. Then I'm going to say, let's use frequency map and call the frequency table of the first window that I care about. And then we're looking at substrings of length k. So I need to give it that k parameter too. Now, this is the only time I'm going to call the frequency table. Once I've done that, I need to say, was there anything frequent? And so to do that, I'm going to have the same test that I had before. So I'm going to range over the values and the keys. So I'm going to range over all the strings and the associated values in the frequency map.items. Okay. And when I do that, I'm going to say, is it the case that val is greater than or equal to t? And s not in patterns. Now, if that's true, then I'm going to append s to patterns. There's another little optimization that I can do though. And what I'm also going to add to this, which is new in this algorithm, is that I don't like this. So when you do this every time through, patterns might start becoming a really big list. And yet to check that s isn't in there, I'm going to have to always keep checking whether or not it's in the list. I can do better than that. Instead of ranging through the whole list in order to check whether or not s is in there, I could create my own way of storing whether or not I've seen s before. And there's I think a relatively simple but clever way of doing that, which is to say, I'm going to declare a map or a dictionary that stores whether or not I have seen a string before that occurs at least t times. Okay, so if a string has occurred at least t times, I'm going to create this map and create an entry for it, and the entry is just going to be true. Okay, So it's going to start off as completely empty though. So I'm going to start off by saying, I'm going to call this found patterns. And it is, I was going to say it's equal to an empty dictionary, but I know how it's going to be represented. And I think it's important to say it's a dictionary. It's mapping strings to Booleans, and it starts off as empty. So each string in here has like a little light associated with it. And if the light is on, then you know that this string has been seen. What that means is I'm going to say if it's the case that the value is greater than or equal to t, I'm going to append it. But also now I want to check and say, is it also the case that I haven't seen it already? And for this first frequency table, I know that I haven't seen it already because I'm ranging over the first frequency table, so there's no way I could have seen it before. So I don't need this check. But what I do need to do is I need to go in and I need to flip on the switch for S. So I need to say go into the map and set found patterns of S equal to true. And the light is now on. So now at any point in time, if I ever, I'm ranging through the genome, I'm 3 million letters down the line, and I see that S occurs again, well, I can just go in and say, well, is found patterns of S equal to true? And if so, I don't want to append it to my growing list of patterns. That's just the first window. So we've got the frequency table, and then we're thinking, all right, but the whole point is this has to be the only, so what are we doing here? This is compute the frequency table for the first window. But if we go back and think about what we're doing, I've got my banana split example. If you were doing this, the idea is we make the frequency table for the first substring of length, window length. And then every time past that, we don't need to make the frequency table again. We need to throw out BAN, and we need to add in NAS, or add 1 to its value, as the case may be. So the point is, how do we implement that idea? And here's where I said this can be a challenging code along, and that's okay. That's the point. We already have a functional algorithm that's going to work if you're willing to wait. But I just want to talk about, in the spirit of we care about how fast algorithms are, how much faster can I make it? Is it worth our while? And I don't know, if it's 10 times faster what we get, that's probably worth doing if we're going to try and apply this to a bunch of different genomes. So let's see. If I go back to my code, this is what I don't want to do. So I don't want to do all of this. I do want to range over the rest of the positions. But at this point in time, I want to add a 1. So I've already done the frequency table for when I is equal to 0. And I should say here, all remaining windows. Okay, so we start at 1. We still go up to, but not including n minus the window length plus 1. And here's where I need to know 2 things. Okay, what is the pattern that fell off? And then later, I need to know what is the new pattern. So let's focus on each one of these one at a time. You tell me, first off, is there a way of saying, and I'm going to call it old pattern. Is there a way of saying, what is old pattern's substring indices? So we know it's text of something to something else. But what is the pattern, so to speak, that for an arbitrary I would plug in values for what goes here and what goes here? So GB said the starting index, that's probably the easier of the two to figure out. It's good to isolate one at a time. If you think about, well, let's go back to my banana split example. When we go from the first frequency table to the second one, what is removed? Well, it's the string that occurred at position 0. In general, if I'm at position I, what's going to be removed? It's going to be whatever was at position I minus 1. So it's nice to just write down that I know it starts at position I minus 1. So far so good, but then I need the upper index, right? What's that going to be? And there's two ways of getting it. There's thinking, oh, I got to know, well, what's the final index going to be? And I find another pattern. But we should know at this point in time, that's not what we do. If I know my starting index and I know something else, in particular, it's a k-mer, it's a substring of length k, what goes here? Say the top index minus the bottom index has to be k. So when I look at this, I'm going to say, well, it's I minus 1 plus k. Okay. So anytime you want a substring of length k, just add k to the bottom index, and you get the top index. I'm going to not write it that way, so Python doesn't get mad. And we know it's just I minus 1 to I minus 1 plus k. While we're at it, what we may as well do is to say, what's the new pattern? While we're in the habit of doing a little bit of pattern seeking. So same question. And I think this one's a little bit trickier. It's something, and then it's something plus k. But the question is, what is that question mark? If we need help, go back to our example before. The pattern that comes in is NAS. At least at this point in time. The next one's going to be ASP and then SPL and so forth. We've got an I to I plus k. Well, if I was 1, this would be A and A, because that would be starting at this. Whereas when I is 1, we're looking at the second frequency table. What we want to get is NAS. So it's not going to start at position I. It's going to start at something bigger than I. And here's where really, yeah, we would want to write this down and say, what's the pattern? There would be nothing wrong if you don't see the formula, nothing wrong with literally writing out when I is 1, this is 2, 3, it's at position 1, 2, 3, 4. And then when it's at I equal to 2, it's at position 3, 4, 5, and so forth. So it's always, in this particular case, it's 3 larger, but then you need to change the window length and change the value of k in order to realize what the pattern is. And in this particular case, the pattern just winds up being, it needs to depend on a few things, right? Because, well, for the new pattern, it needs to depend on I. We got that much right. The longer the window length, the bigger it's going to be. So that's going to make, if the window length is big, the new pattern is going to be farther out to the right. So it has to be somehow dependent on window length. And the other thing is the longer the value of k, that's going to push it backward within the window. And so we need a minus k. And it turns out that that's the pattern that we have. So it's this whole thing, I plus the window length minus k at the start, and then that thing plus k, but then that minus k plus k will cancel out. All right. Those two things alone are plenty challenging. And now we do the work of updating the frequency map. And I like the idea of keeping these things together. So let's update the frequency map. So I've got my table, and the first thing I'll say is, okay, well, the old pattern fell off. What does that mean? I saw in the chat, great, we know what it means to get rid of the old pattern. We may not be getting rid of it. So for example, if I look at my example from before, I need to stop scrolling. I should just probably copy this down. Let's do this so I can appeal to it beneath here. Okay. We're updating the frequency table. And in this case, well, I got rid of band, but band could be like 14. And then if that were the case, band would be 13 down here. So it's not quite right to just say get rid of it. The first thing I would say is subtract 1 from the value of the old pattern. So I'll say, I know how to do that, frequency map of old pattern, and then minus equal 1. So I'm simply subtracting one from it. But if it's 0, then I don't want it to hang around. So in this particular case, I don't want to do, oh, it's 0 in the new frequency table. So I would not want to have BAN and 0. Anything has an occurrence of 0. So if it has a 0, what I really should do is get rid of it if it's 0. So if it's the case, so when you look at frequency map of old pattern, and that's equal to 0, okay, throw it away. So we know how to throw away an element of a map. Just like we deleted Florida, we're going to delete frequency map of old pattern, but only if the value is equal to 0. So that part of the frequency map is updated. Great. The only thing to do is now update the other side of the frequency table. And so if I'm updating the other side of the frequency table, what I want to do is to say, well, I want to add one. So if we look at our example, I have NAS. I want to add one to it, but if it doesn't exist, I want to set it equal to 0 and then add one. This is actually the exact same line of code that if you look at helper and look at our frequency table, we've done this before. So I've done this before, and I say frequency map of pattern is equal to frequency map dot get of pattern 0 plus 1. So this is the same exact line of code. Dot get says go in and try and access frequency map of pattern. If it exists, great. So if it exists, go in and get it and then add 1 to it. If it doesn't exist, set its default value equal to 0 and then add 1 to it. So I'm just going to take that single line of code that I have in the helper function, and I'm going to say frequency map of not pattern, but in this particular case, new pattern is to do the same thing. So this is add 1 to the value of new pattern or create its value equal to 1. This is doing quite a lot of work here, right? But what it's not doing is pretending it doesn't know the frequency table, so it's only actually changing 2 strings. And the code gets longer, and the hope, knock on wood, is that it's going to get faster too. So that's what we need to try and see. We've got the new frequency map. The whole point is now the frequency map is updated. Great. Okay. Whew. Regardless of how closely you followed that, we know we've got the frequency table updated. What do we want to do? We want to say, what is frequent? Okay. That we haven't seen. So we know how to do this too. I'm going to say, is it the case that frequency map of the new pattern, and actually one of the things I could do would be to say range over the frequency map and identify everything that is at least equal to t and hasn't already occurred. And I could go ahead and start writing this for s, val in frequency map dot items, and I could range over everything. And that's perfectly reasonable. But I want to point out that there is something that we can go ahead and make faster. Here's an opportunity for premature optimization. In other words, if you look at the first frequency table and then you make the second frequency table, remember that they're very similar. And I have a question, which is, if it's frequent in the second frequency table, if it's frequent here, well, there's 2 possibilities. One possibility was that it's frequent in the previous frequency table. So ANA, for example, if your threshold value were equal to 2, it's frequent here, but you only changed 1 kmer, so there's a good chance it's still going to be frequent here. There's one possible case, though, where something is frequent and has not already been captured by the previous frequency table. Because remember, I don't care about these duplicates. If I found ANA once, I do not care about trying to find it again. This is the whole point of me using that dictionary to say flip the light on associated with each string to see if I've found it before. So for a string, if ANA were in this frequency table, I would not want to add it again, and I don't even need to check it again. There's one thing I need to check. So here's my question for you. What is the thing that I need to check? What do we need to check? I've got something in the previous map that's frequent. Good chance it's in the frequent in the new map. Even if it's not, I don't care, because maybe like old pattern fell off and that's what caused old pattern to not be frequent. But again, I don't care about old pattern. There's only really one possibility here. That possibility is new pattern all of a sudden is frequent. This is a really clever idea. And this is the sort of thing that can also really improve our algorithm, because not only do I not need to make the frequency table brand new every time, but I also don't need to range through the frequency table every time, because I know that these two things are so similar. The only way that I could find something that's frequent in here that I haven't already seen is if it's this thing. So the only thing I actually need to check is this new pattern? Is it frequent? And so this is where I don't even need to range over the frequency map at all. Because if case 1 is satisfied, I don't care. It's already been identified. So the new pattern all of a sudden is frequent. That's the case I need to check. We don't need to check 1. But we do need to check 2. And here's where I say, is it the case that frequency map of new pattern at least equal to t? I know it occurs at least once because I know it's in the frequency map, but is it at least equal to t? And if so, I want to say patterns dot append new pattern. But I want to be careful because maybe I'm 3 million letters down. And I realized, well, I've already seen new pattern 1 million nucleotides before this. So I don't want to necessarily append it in that case. I want to say, well, the first thing I want to check is the light. So check if new pattern is already in our patterns. And I will say, to do that, I need to go, is a key already equal found patterns of new pattern. So have I seen new pattern already? And I know that that is how I'm using this dictionary, found patterns. All right. And that's so close. But we saw this when we first started working with dictionaries. You've got to be careful with dictionaries if you access something that doesn't exist. So if it has been found, then sure, you'll get this equal to true, but it might not be in that dictionary. So if that's the case, I need to say, well, how do I check this? And in this particular case, I'm going to say found pattern, not found patterns of new pattern, but found patterns dot get. And in this case, it's going to be new pattern false. So go in and try and access found patterns of new pattern. And if it doesn't exist, it's going to be set to false. And that will add an entry for it, but it's not going to add an entry for it that's equal to true. So this might be like slightly inefficient, but it's not going to flip the light on. It's just going to say I've seen it at this point in time, and I've at least checked it. And if it's greater than or equal to t, and it's the case that is key is equal to false, okay, so I have not seen it thus far. is key would be false if I've not seen it. Or if I could just say not is key. Okay. Either way. Then I'm going to append it to pattern. All right. And I need to do one more thing. I need to say flip the light on. Every time you find something that's new, you got to flip the light on. Found patterns of new pattern is equal to true. All right. And what I'm trying to convey here is that this is not obvious at all. I don't think. If you think it's obvious, you're smarter than I am. I think this is pretty neat. It took me a little bit of work to even find the optimization. I think it doesn't occur to you initially. And the only reason it can occur to you is because, well, you wrote the simpler version of the function, which may not be that much slower, but it's not obvious whatsoever. And especially this little check that at the end of the day, I don't need to check all the values in the frequency table, that because they're so similar, the only thing that could possibly be new is new pattern. That's pretty cool. So I love this kind of thing, but I do want to point out one thing, which is that remember in our original find clumps function, I said you could make all of this like a subroutine, and I love code like that. The challenge is if you do that, then you wind up missing the optimization in this case. So the optimization depends on you not using the subroutine, because the subroutine assumes that you're making the frequency table anew every time. And so in this case, you wind up with a function that's longer. And maybe you could squeeze a subroutine in here somewhere, but it's not clear that it's going to make it tremendously shorter. So returning to what I want to do, we have two approaches. We have an approach that seems completely reasonable, that honestly, Python is on average, something like 200 times slower than C++. So if you all were like, oh, we love C++, we want to have programming for lovers in C++, the function would have been written 30 minutes ago, and we wouldn't have needed to do all this brilliant stuff. So a lot of times with Python, it's forcing you for the optimizations that you need because it's just so darn slow. That having been said, it was at least a cool thing to see. And it's going to be really disappointing when I run this and it's like 1.7x speed up, right? So let's at least see. We know how to time code. And one of the things I need to do is to go into main, and I need to have all of my timing code. Now we've got timing code from our work with primes. And so timing code should be, I think, really straightforward for us at this point in time. I don't want to spend a lot of time on a code along establishing timing code. And so what I want to do is just give you some timing code here. Okay. So here is some code to do the timing. How does it work? As we've seen before, you start your stopwatch. Now I need to import time in order for this to work. But we start the stopwatch. We call find clumps on what we care about. We have the amount of time that's elapsed, and then find clumps took however much time here. And then we have the second algorithm. We print how long it took, and then we print the speed up, which is the ratio to the knock on wood slower algorithm to the faster algorithm. So you take the ratio of the runtime. So whatever is slower divided by whatever is faster, and that tells you the ratio of how much faster they are. So there's our code. Everything should be in order. The one thing I want to do is to say, let's ignore this for a second, because I want to find clumps in E. coli, but not yet. So what I would like to do to run a fair comparison is, I know this is going to take a long time. I'm just going to take the prefix. I could take any substring I want, and let's have it be length 100,000. Okay, and then I'm going to time the two algorithms. So I'm only looking at the first 100,000 nucleotides. As we saw before, when we ran this clump finding algorithm, the slow version, it was pretty fast at doing 100,000 nucleotides, so I feel like it should finish in a few seconds. What do we think the speed up is going to be? Do we have optimists or pessimists? How much faster do you think our find clumps faster algorithm is going to be? Give me a number. Much faster? Here's where we really could dig into the algorithms and think, what is it that... Yeah, it's going to depend, BZ, that's a good point. It's going to depend on a lot of things. So it's parameter dependent. We should run it on a bunch of different parameters. This is a practical value of window length equal to 500. You could think it's going to depend on these things. So the longer the window length, the bigger the frequency table, right? So if we're only making the frequency table once in the faster algorithm, and then I'm not ranging over the entire frequency map in order to find is the value of everything greater than or equal to t. So you're right that the speed up really should be a kind of proportion to the frequency table. We've got some different thoughts. 3x, extreme pessimist there. 10x for minutia, yeah. But extreme optimist Lori says 500. I think the idea is the best it could be is 500 because the window length is 500. So at every point in time, instead of making a frequency table with 500 substrings in it, you're just adding a couple. And so, yes, it absolutely depends on the genome and the window length. I think the window length is the critical parameter here. I think what we'll see is let's do it for 100,000, and then I'm going to do it for like 10,000 and like 20,000. And I bet the speed up is going to be kind of comparable. I don't actually know. So let's see. I'm going to run python 3 main.py. And the prayer, really the fervent prayer, is that I don't get a runtime error because this find clumps faster algorithm is not exactly short. So let's see. I'm going to close my eyes and pray. Okay, I open my eyes. So far, everything's all right. So it's timing the find clumps algorithm, and then it ran find clumps faster. And you notice it all printed immediately because find clumps took about 6 seconds. Find clumps faster took 0.03 seconds, and the speedup was about 200x. So this hypothesis that we had, it's not going to be quite 500. It's going to be better than like 3. It works out pretty good, 200x. And then, of course, yes, does it change with the window length, right? You're starting to get the right thoughts, which is that parameters affect things. You shouldn't just take it as equal to 200. So let's make the window length, I don't know, 5,000. So if you have a huge window length and you run this, that actually is probably going to slow down. Maybe this was dangerous. That's really going to slow down the slow approach. I'm going to control C, and we're not going to do that. But I'm going to take it to 50 at least. So when the window length is smaller, the speed up's only 20 times faster. See, it's almost like an exact power of 10, which makes sense. Let's take it to 10,000, and I will do 5,000. So that should be kind of fast. In theory, even though the genome has gotten shorter, the window length got a lot bigger. So you see the speed up is 104 times. Here, when it's at 500, the speed up is only going to be 20 times. So the longer the genome, the faster it is, and the bigger the window length, the faster it is. Makes a lot of sense. So here we see the next idea, like if we're thinking big picture, we're trying to compare algorithms, and I'm really pointing us to topics that are well beyond introductory programming, but I think you're plenty smart enough to understand what I'm getting at here, which is that the speed up now depends on different parameters. That makes a lot of sense. Okay, so we'd seen that before, that sometimes it depends on like n for primes, but in this case it's depending on two things. It's depending on the genome length, and it's depending on the window length. There's one more little optimization. So I want to take it back to what we had before, which is 500 and 100,000, where our speed up was 200x, because someone said we need to make sure that we're using why don't we use a set? If we care about duplicates, so I'm going to go into find clumps faster, and I care about not actually adding duplicates to my collection of patterns, then the way to do this is to use a built-in data structure that Python offers called a set, which is a great idea. So Python has this set data structure is kind of like a list, but the point is that the elements are not inherently ordered. And also, you're not allowed to put something in there that you already have in there. So it's like a duplicate-free collection of things. It's a nice data structure. The downside is then you have to know it exists, and you have to get comfortable with appreciating like when to use it. And we have an algorithm that's already plenty fast, but maybe it's the case, right, that using this Python built-in thing is going to help us out. So instead of declaring patterns to be a list of strings, at the end of the day, I'm going to return a list. So I'm not going to change the fact that I'm returning a list of strings. But what I want to do in the meantime is to declare it not as a list, but I want to declare it as a set of strings. And when you declare an empty set, we run out of parentheses and characters in order to represent empty things. So like we can't use braces because that's a dictionary. We can't use brackets because that's a list. We can't use that because that's, I guess, an empty tuple. And so the only thing that we can do is just to say set. All right. So set of strings is equal to an empty set. And so the sets are unordered and don't allow duplicates. That's nice. So we need to change that. The other thing is we need to say, where else are we really using this? Well, the other thing I now need is not to have found patterns, because the set is going to include this built-in thing that's going to say, is this in there already? And that's nice. So you don't actually have to keep track of this dictionary of things where you're flipping the light on each time through. In the first time you go through the frequency table, like we made the frequency table, and this is for the first window or whatever, and then we range through and we say, is it the case that the value is greater than or equal to t? Before we said set patterns.append of s, but in this particular case, we're close. Python has to be special. We're not appending to a set, we're adding an element to a set. It's the same idea, just that the notation changes. And then I no longer need to switch flip the switch for s, because the set is going to store whether or not something has been seen, and it refuses to add anything that's already there. Cool. And then the next thing that we do is we need to say, well, instead of checking when we go down here, so I've got the new pattern and the old pattern, I update everything in the frequency table. That doesn't relate at all to patterns. Down here I say, well, I don't need to do this at all. Okay, so I don't need to keep my fancy dictionary, and I don't need to flip the light on. I'm keeping all this commented in case you want to uncomment it out later. But when I do patterns.append of new pattern, I don't care about this anymore. I just say, if it's at least equal to t, like check the frequency map of this new thing that we're looking at, did it go above the threshold? And if it's above the threshold, I'm just going to patterns.add it. And then at the final point in time, I would say, well, I want to return something that's sorted. And so just for the sake of niceness, I'm going to take my set and I'm going to convert it to this sorted list of things. And then everything's going to be fine. Again, one more little optimization. The question is, does it give us an improvement, right? We have this nice built-in operation. I was adding this bulky thing that's this special dictionary with the light switching on. We've lost some lines of code. So when I save this and I run it, hopefully we're going to see an even bigger speed up, right? And so what are our values? We're going to keep the same values as we had before. In def main, we said we're running this for the first 100,000 nucleotides. Window length is 500. T is equal to 3. K equal to 9. Same parameters as before. We'll run it. We know it's going to take about 6 seconds for find clumps. And yet our speed up doesn't necessarily improve. Okay, and I think that this is probably dependent on kind of the internal state of the computer. So you're going to get some slightly different numbers. And I think I may have, so for whatever reason, I mean, my computer is also running a stream right now. So there's a good chance that there are some things competing for resources or something. But on the whole, when you run this multiple times, what you're going to see is the speed up is still about 200 times faster. So even though you have this set with these nice built-in operations, it doesn't really make the algorithm any faster than what we did before. Which is funny, because then it's like, well, you're telling me I don't even need to know anything about sets in Python. I could just make a list and then also have a dictionary associated with it. And every time something goes in, I could just set the list value equal to true, and I could kind of implement it myself. And the point is, yes, that's right. A lot of people who might work with sets would think, oh, this is this very fancy thing, but you don't actually ever even need it when you work with Python. Although I'm not going to deny, obviously it's a convenience. So we initially, let's not lose track of what we're going to do, because we still have one other thing to do. And what we want to do is apply our algorithm to the full genome. So we've got our timing code, and that's good. But what we care about, and I'm going to knock this down by a factor so I can keep my timing code in there. What we really want to do is call the clump finding algorithm on the full genome. We've got this thing that's much faster than what it was 200 times faster for the first 100,000 nucleotides. It's going to be even faster when you run it over the entire genome. So I care about what I had up here. I think I lost the code, but we want to set E. coli clumps equal to what happens when you run the faster algorithm, and you call it on genome, K, window length, and I've already set these parameters, so it's okay, and T. So all these parameters were just set up here. And then at the end of this, I want to say how many clumps are there, and I could print them all out, but for now I'm going to say we found, and then I'm going to say length of E. coli clumps. I'm going to say total clumps. And I probably should print the exact values of K, include that in the print statement, which would just be a nice thing to do. But I'm not going to run this on a bunch of different values. I just want to show you we finally actually get to run our code. And remember what we're doing. We're trying to find everything that clumps together in a window of length 500, of length 9, that occurs at least 3 times in that window. I'm going to hit run. And what do we find? We find 1,904 total of these substrings. And the question is, what does that tell us? Like, what does this tell us that we found 1,904 total k-mers? What does this mean biologically? We found 1,900 of these clumps in the E. coli genome. There's 2 answers. BZ says there's 1,904 clumps of length 9. That's certainly true. But I mean, on a meta level, what does this tell us? They could be junk. Maybe. There's not a lot of, if you stay around for great ideas in computational biology, there's not a lot of junk in bacteria. Like we carry a lot of these repeats in our DNA and things that aren't necessarily useful. Bacteria don't have the time and energy to deal with that. Yeah, so good answer, I see. All these clumps, they mean a lot of different things. It means there's tons of repeats in the genome, and not just in the genome having throughout repeats. I'm saying there are a ton of clumps in the genome, meaning there are a ton of small locations that have a bunch of repeated strings in those locations. So if we were hoping to find like regions of interest with identifying things that clump together and say, oh, here are the locations where there's high probability that there's some protein that's binding to the DNA, we're in for a rude surprise, which is that this is extremely common. And if we wanted to find like specific regions in this way, there's nothing special about one region versus another. This idea that we're going to have clumping occurring throughout the genome, it's going to be everywhere. And doing this for E. coli was nothing special. You can go and get your favorite genome from somewhere else, and then let us know, like come to the Discord and do this. Tell us how many clumps you found for different parameters of these other bacteria. Nothing's stopping you. You got all the code. But for now, what I want to say is, if you're looking for a specific region of interest, the clumps are just not going to help you. All they're telling you is that there's a lot of stuff. So I took the detour to optimize our algorithm. But I think that algorithm is beautiful. But the issue is, for what we're doing, we optimized for kind of the wrong problem. And if I'm looking for something hyper-specific, I need a custom tailored approach. So we're going to do a much shorter, don't worry, we're going to do a much shorter collection of code to look at one specific application. And the specific application that I'm going to find is, how is it we can figure out where is it in this bacterium's genome that it initiates the replication process. This is where we started when we generated the frequency array, or the frequency table in the first place. It allowed us to find, if I know what the replication origin is, what's frequent. How many times does each chimer occur? What I really want to find is, how is it that I would have identified that region in the first place? And the point is that the clumps are not going to help us with that. So let's take a different approach. And what will be nice is that after you've lifted these heavy weights of looking at that optimization of the clump finding, this should feel so natural. And this is what you're going to see as you go through programming. A lot of the times, as you get stronger, always then go back and try and do something that you've done before. And what you'll see is you're going to gain more and more comfort. I think a lot of people eject from programming because they think, oh, it's getting harder and harder. But yeah, if you give yourself the opportunity to go back sometimes, you'll see how far you've come. So in SRC, I'm going to create a folder called skew. And in there, I'm going to create a main.py, not main.pui. Let's try that again. Main.py for Python. And I need a little bit of starter code, so I can go into my, I just write clumps. And I need my 2 lines at the bottom to say run this thing. And I'm going to say def main. And in def main, I'm going to say print skew arrays for finding replication origins. All right. Now the setup here, and I would encourage you, if you haven't done the reading that accompanies this chapter on our Programming for Lovers website explains all of the biology here, and you can delve deeply into understanding exactly why this is the case. But there is a high-level idea. And the high-level idea is that the bacterial genome is a circular chromosome. There is some point on that chromosome where it initially opens if it's going to replicate its DNA. And then as it opens, it replicates in both directions. So it expands outward from that point. We want to start, so we want to find where, for this one specific biological application, where the replication begins in the bacterium using just its strings of A's, C's, G's, and T's. And fortunately, because we know a little bit of biological context, the half of the genome after the replication origin spends its life single-stranded more often. And the reason why is as it opens, because of the directionality of the DNA polymerase enzymes that replicate it, again, check out our reading for all of the precise details around this. Half of your genome, this bacterial genome, when it opens, is going to spend its life single-stranded waiting for the DNA polymerase to come replicate it, and the other doesn't. So what will happen is, as a result, there is a common C cytosine, which eventually goes into thymine mutation on single-stranded DNA. And so the result is that after the replication origin, there's a shortage of C and normal guanine. Okay. On the other half of the genome, there is normal C, and there's a shortage of guanine. And there's technical reasons for this that the reading gets into. Okay. But the idea is, just before and just after the replication origin, something very fundamental changes about the genome itself, which is that right before, the DNA spends a lot of its time double-stranded. Right after the replication origin, the DNA spends a lot of its time single-stranded, which makes it more susceptible to being mutated. So what our idea is to plot the number of G's minus the number of C's that you see over the genome and look for a change in this. Okay, that's what we're going to do. So the first thing I'm going to do is I'm going to write a function called skew array that's going to store this plot. It's going to be very similar to what we did when we counted primes. We're going to keep track of something up to a particular position k. So I'm going to say skew array is my function. And what does it do? It says we're going to have as parameters, we're going to have a genome, which is a string. And what it's going to output is going to be a list of integers. And this list of integers is the skew array of the genome, where position k is equal to the number of G's minus the number of C's encountered up to this point. And I'll say, what does this do? This computes the skew array of a given genome. So this is the GC skew array. I'm going to take as input my genome as a string, and I'm going to return a list of integers. So far, so good. I can do some error checking. The error checking here, thank goodness, is quite straightforward. I only have a genome. If the length of that genome is equal to 0, I need to raise and value error and say empty genome given. At this point in time, everything's going to be good. So what I want to say is, how long is that genome? Probably helpful to set that equal to some variable n. How big does my skew array need to be? Well, I'm going to have a special value of 0 at the start. So I'm going to have one extra value. So I'm going to set it equal to 0 times n plus 1. We know how long it's going to be in advance. The next thing I'm going to do is I want to range through the genome and compute skew, let's say I. And skew of 0 is going to be 0 because that's our starting point. And then I'm going to keep going and say at position I of the genome, what's the number of G's minus the number of C's I've seen. The slow way of doing that is I'm at position I and I go all the way backward and count everything. The smart way of doing it, using what we just learned with optimizing and clump finding, is to just learn from that and say, well, I'm at position I. The skew array of everything that I've encountered up to this point is all I have to look at plus what the current contribution is. So I'm going to say for I in range of 1 to n plus 1. If it's the case that I look at genome of I minus 1, and here's where, actually, let me hold on to this for a second. What I do want to set is skew array of I is equal to skew array of I minus 1, and then like plus the contribution from I. And here is a fantastic way, we've seen a lot of things connect as we've gone through this chapter. And one of the things we introduced was these like little dictionary literals. And this is a fantastic example of when we could apply one, because I could write a lengthy, not that lengthy, but if else or match, but instead we will use a dictionary literal. Okay, I'll show you what I mean. I'm going to have a dictionary literal that's going to be called skew. It maps strings to ints. And what it's going to map in particular is aid has no contribution. Every time I see a C, though, if I'm keeping track of the number of G's minus the number of C's, every time I see a C, I'm going to drop the count by -1. Every time I see a G, I'm going to add 1 to the count. And every time I see a T, I'm going to keep it the same. What's nice about that is that then I say, I just need to access the dictionary, and the contribution from I is just skew of the current symbol, which is genome of I minus 1. We need to be careful and make sure that we appreciate why that is. It's because we start I at 1, and we want to access, well, the symbol at starting at position 0. So we need to go one symbol backward each point in time. That would be a very easy off by 1 error to make. I'm just pointing it out. And we need to be maybe a little precise. So I could have an error message here that says, I want to make sure that when I access genome of I minus 1, remember that's just a symbol. It's an ACG or a T. And I hope that it's an ACG or a T. So if it's not in a key in this dictionary, I want to have a value error. If it is a key, that's when I'll do my formula. And so here I'll say otherwise, I'm going to raise a value error and say invalid symbol given. Okay. Right. So is this symbol one of our keys here? If so, go in and access the value that's associated with it and add it to whatever the previous one was. Okay. So let me show you what I mean, just as a quick example. If our string is like GCC AT GC AA, okay, and you're at position, I don't know, you've done the first 5 things, okay, so skew of 4 is equal to the first 5 symbols, actually 5. And that's the number of G's minus the number of C's. So it would be -1. It's the exact same idea as what we saw before with shifting over by 1, except at this point in time, you'd say, what is skew of 6? Skew of 6, and you say, oh, I need to go in and I need to count how many G's minus the number of C's there are up to this point in time. But you don't really, because I could say it's 2 minus 2. But actually what I need to do is just to say, well, I've counted them up to here, and I see a G. So if I see the G, I just add 1 to what I had before. So it's -1 plus 1, which is equal to 0. So that's what I was getting at with this efficiency that we add to the algorithm. And in particular, then we look at what's skew of 7. And skew of 7 says now I need to take this C into account. And I could say, oh, I count up 2 G's and 3 C's before me. But really all I need to do is just say it's skew of 6 minus 1, which is equal to -1. So it's the same idea. Don't reinvent the wheel every time through. Just use what you've already computed. And we see it in 2 like seemingly completely different contexts here. So this is all that function is doing. At the end of this process, we get down here and I say, I forgot, I need to return my skew array. So I said that's what I was going to return. And at the end of the day, all it's doing is storing the number of G's minus the number of C's I've seen. We should visualize this thing as well. And here's where I'm going to have a little bit of code that's going to plot this. And I want to do the same thing that I did when I looked at primes. The x-axis is going to be the position in the genome. The y-axis is going to be the skew value. And I just want to connect the dots. Okay, I connected the dots into my microphone. So we just want to connect the dots. And then we're going to look at this picture. And if you've seen the reading, you know what it looks like and you've already been amazed. But we're going to make it and you're going to be amazed regardless. So I have a little bit more code here for drawing. And what's nice is I have a function called drawSkew. It takes a skew list and it's a list of integers. It's not going to return anything. And I'm just going to be very, very lazy, which as I said is a virtue. And this is just going to draw a skew diagram using a skew array. And I may as well call this, for the sake of simplicity, I'll call it skew array. Okay. So I could check, make sure it's not empty, but I just have a few pyplot commands. So if you've been with us before, we've worked with pyplot for making these line graphs. And all I have to do is make sure that I have from matplotlib import pyplot. And that will import just this sub package from matplotlib. If you need to install it, you can pip3 install matplotlib. Okay. I already have it installed, and you probably do too. And now in my function, I'm just going to say, I'm going to make a plot. It's called skew array. And that automatically makes a line graph. So this automatically connects all the points. Because the y values are the skew array values, and the x values by default are going to be the integer indices of the list. So it's nice that this is such a common thing to just connect the points of an array that it's just one line function. But we're going to say we need to also give it a title of skew diagram. And I'll say, yeah, we don't know what genome it is. We also then need to give it a little bit more. So we are going to say, what's the X label? this is the genome position. So as we go along the genome, like what is our current nucleotide? And then what's the Y label? Well, we say that's the skew value. So that's the number of, I should be more precise here. I'll say number G minus the number of C encountered up till now. Okay, that's a really bad y-axis title, but it at least is explanatory. And then I'm going to say save the figure as skew diagram dot png. And I also am going to show this thing. So I'll go ahead and automatically save it, but then I'm going to show it. Now, when I save this, the only thing that's remaining to do, I've got some functions. I probably should run them. And I want to do the exact same stuff as that we had before with processing E. coli. So a lot of this stuff is the same. When we go into our clumps file, I'm just going to copy over a little bit of code because it's going to be the same thing that we did before. I'm going to access my URL, make sure everything is okay, raise for status, and then access the text. So all that's going to stay the same. We know that this will work. And when I go into main, I'm going to copy it and say our URL is this string requests.get, which means I need to make sure that I have requests installed, but then imported at the top of the Python file. So I'm going to say import requests. And then raise for status, access the string as a text. Now Genome stores that. And so what do I want to do? I want to say that, well, this is the E. coli skew array is equal to, let's call this skew array function that I wrote of the genome. And then what do we want to do? We want to draw it. So we want to draw a skew of this array. And then at this point in time, I'm going to say skew diagram drawn. And that will be an indication that main is finished. So now we're ready, right? And we went through this quickly, largely because once we understand the idea of what we do, yeah, there's a little bit of cleverness here. I'm not going to lie, just because Python is slow and we can't, at every point in time, we can't waste the time counting all these G's minus C's of everywhere before us. But hopefully this is starting to feel comfortable, right? In the sense of being able to go through something like this, and you've seen just how far we've come already, hopefully in a short amount of time, with being able to understand how all of these different data structures and constructs are fitting together into one coherent piece. So if you made it this far, good job. I'm proud. And let's at least look at the skew array. So all I have to do is python3.main.py or python main.py on a Mac. I'm running clumps. I'm not even in the right folder. Okay, so this is hard on me too. Let's go up a level, and we need to make sure that we're in the skew. All right, Python 3, main.py. Name PLT is not defined. What did I do? I defined something PLT. Okay, let's see. PLT.show, that doesn't sound good. Line 75. Okay. pyplot.show. That seems reasonable. Let's try that again. All right. And now I've got it in two places. So it pops up on my screen, which I can close out. But it also, I told it to draw this as skew diagram.png. And we remember. So I'm going to show you the skew diagram. But we're going to remember one thing, which is that what is it that this is going to show us? What do we hope it shows us? As a refresher, we want to find where the replication origin begins. We know that after the replication origin, there's this mutation of C's. So we lose C right after the replication origin. And this is true of bacteria in general. It's not an E. coli thing. You're just going to bleed away some of the C. Some of the C winds up being important, but you're going to lose some. But right before the replication origin, it's an opposite circumstance. So you have a shortage of G for technical reasons, but you at least have normal amounts of cytosine, or C. So our idea was to keep track of the numbers of G's that you've encountered as you go through the genome, and the number of C's that you've encountered as you go through the genome, And we're going to have an array of this count that we keep track of. And now all we've done is just connect the points of the array. So when we look at this, I'm going to ask you to tell me, what do we see? And then what's the replication origin? Here it is for E. coli. What do we think? Certainly it's a stark picture. Some good answers. Okay. So now if we have a shortage of C right after the replication origin, then if we plot, but normal G, if I keep track of the numbers of G minus the numbers of C, what's going to happen is right after the replication origin, that shortage of C all of a sudden is going to cause the numbers of G to outnumber C. And so you will start seeing an increase in this numbers of G minus the number of C. Right before then, it was the reverse situation. You didn't have as many G's. You had a shortage of G's and plenty of C's. So when you look at G minus C, it's going to have a negative slope. So as a result, your replication origin is just right here at the minimum of this table. Right. And again, if you want all of the biology behind that, go read our chapter. We've got an entire explanation of how this replication process works, exactly why it's the case that you have this process of C's mutating into T's and why they're single-stranded, why this DNA spends a lot of its life single-stranded and susceptible to mutations. Like, why would such a thing be the case? And it's because of some beautiful molecular biology and understanding how it all works. But for now, I want to point out, we found the replication origin here. I could leave you an exercise. So again, if you're here and you want to feel confident, something that you could do is to say, all right, I can look at the picture and I can feel comfortable that it's around position 4 million. Cool. But I know plenty enough to write a function that will find those positions. And this is just a practice exercise. So I'd say, here's an exercise, is to say, I want a function called minimum skew indices. And it's going, I don't know what I just did. It's going to take as parameters, it's going to take a genome as a string, and it's going to return a list of integers. And that list is nothing more than the collection of indices, okay, meaning the indices of the list of the skew array. And let me do an additional point. Collection of the positions in the genome where its skew array achieves a minimum, right? So in this particular case, it might tie, right? So you can imagine it bounces all over the place and it hits the minimum multiple times. But I want to find what is that position. And in particular, it might be more than one position, might be like 3 or 4. So if you zoom in on this, right, you could zoom in enough to imagine that there's going to be a little bit of bounce. So what is the precise position where this happens? And so what this does is it finds the indices of a genome where the skew is at its minimum. And so we're going to have a genome as a string, and we're going to have that this returns a list of integers. Pretty good. You can write this as my point. You can identify what the errors need to be. You're absolutely going to need to call the skew array function. That's going to be helpful. But this is like, again, getting comfortable with this and adding this into what we have in main so that you're able to identify, after you call this function, you could say like positions equal min skew indices of genome. And then you could print that the positions achieving the minimum, or I could say, or likely position of that are candidates for the replication origin, and then print the positions. And it'll tell you something that's about 4 million, but you'll find the exact positions. What's neat about this is that this picture, you might think, oh, well, you gave us a picture that just happens to be very pretty. It's not that way at all. It's one of the rare examples in biology where this phenomenon is so prevalent, it's universal across all bacteria, that just past the replication origin, half the way around the genome, all that DNA is single-stranded for some of its life. And there's enough of this C mutational pressure that in all bacteria, essentially, you're going to see a picture that looks like this. Again, if you don't believe me, you can do the same thing. Go grab your favorite bacterium, post it to the Discord. Guess what you're going to see? You're going to see this V-shaped plot. So you can go do that. And the other thing I would say is, as we wrap up, we don't need a complicated algorithm to find something real. There's a whole lot less code here than there was when we wrote all of that clumps code. And at the end of the day, the clumps code kind of led us down a path that didn't lead to anywhere other than saying biology is hard, and there's tons of places where within any bacterial genome where there's probably at least candidate sites for these repeated strings that serve as binding regions. And that's certainly something that we find useful. But here's an example of literally solving a biological problem with some straightforward, maybe the first type of analysis you do, which is to count up the number of letters that you see. This plot, and I'll let you finish out with writing the minimum indices function. This plot summarizes computational biology, the dream of computational biology, and what it is in a nutshell, which is that actually finding this region using an experiment in the laboratory, it's going to require a lot of human labor, time and energy and resources and kits and all that stuff. And if you think about, like, we could have thousands, millions of different variants of bacteria that we might want to study, you're simply never going to have the resources to run this experiment for thousands of separate times. It's a worthwhile thing to know, just as anything in the genome is worthwhile to know. Like, where are the genes in this thing? These are the sorts of things we'll talk about in Great Ideas in Computational Biology. Where are the genes in this thing? What are the other regions that we might study? We're at the tip of the iceberg. This kind of looks like an iceberg. But we're at the tip of the iceberg in terms of the questions that we can ask and answer about this. But my point is, we have answered one small but meaningful question here that we simply probably would never have the resources to run the number of experiments for every bacterium we could care about. And yet, if we use data analysis and write a little bit of code, we answer this question for every bacterium in the history of bacteria that's had its genome sequenced. So as long as we have the DNA data set for it, we get an immediate answer for thousands of bacteria, like instantaneously. And that's pretty cool. That's a great endorsement for computational biology as a field, but I also hope it makes you want to stick around for Great Ideas in Computational Biology with me, and that I think it's a good plug for the larger field of what we look at with bioinformatics algorithms. So that's all for biology for now. We're going to come back to biology in our course, don't worry. But for now, I think that's going to conclude our work in this chapter. And I will plan on seeing you next time. Thank you for joining me. And until I see you next, happy coding.